so a couple of things here with regards to the key for these questions. I talked just at the end of the class that so at the end of yesterday's class, I think it was Ben who had done number 7, and he was getting a number in the neighborhood of 70 grams. I'm going to keep that solution I have up there, which is 58 to 62. That's what you get if you determine the equation of the line of best fit, which includes the y-intercept, on your calculator using the regression. When you read it, it's interesting how just a little tiny change in that reading makes a difference. So I can't remember. I think the y-intercept when you do it with the calculator is like 0.63 or 0.61 or something. And yet when you read it, if you read it as 0.7, that's going to change your answer significantly. So what I would say to you is that anytime you have a question where you're dealing with this and it's an exam question, you have to put your faith in me and the Department of Education that their answers that they accept are a fair range of values. You're not going to get ripped off because you read it and the person who made the key did it on their graphing calculator. So I would say there are 2 answers here. One is the one given, which is 58 to 62 grams. And that would be a range of acceptable values if you got it on your calculator, if you got the y-intercept from your calculator. I would say another range would be 68 to 72. And that would be if you read it. But I tried my best, and I can't see how you would get something like 65 or 66. It'd be very difficult to get those numbers. Anyway, let's take a look, please, at the questions 1 to 7. Take a look over your work. See if you have any questions you would like me to go over, and we will go over them, and then we're going to move on today. Arden. Number 7, absolutely. So in order for me to explain number 7, what I'm going to do, first of all, is just explain the whole principle in terms of the physics of what's going on in this graph. This force is the downward force being measured by the scale. And the reason why the scale has a reading, and this goes back to this diagram that you picked, the correct answer here would be B. The reason why it has a reading is the force of gravity is pushing this against the scale, and the electric force is pushing it against the scale. So the scale is pushing back up with an amount equal to both of these added together. And this force subscale is actually what's being measured, and that means that that's actually what this is. So I'm just going to make a note here that this force is actually the force due to the electrostatic repulsion of the spheres plus the force due to gravity. It's those 2 forces being added together that are giving you that scale force or that measured force. By the way, I can include vector symbols there because they're both in the same direction. So when I add them, I just add the numbers. What this means is that that force that's on the graph is the electric force plus the gravitational force. I put the electric force here because it's KQQ times 1 over r squared, and I'm going to be doing a comparison here to the equation of a straight line, which is y equals mx plus b. And the reason I put the electric force here is because x is in the electric force. When you look at the graph, x is the reciprocal of the square of the distances, or the square of the reciprocal of the distances. It doesn't really matter which one you choose. And that's contained in Coulomb's law. Then we have, let me put F here again. Then we have plus, this is m times g. So when you compare, I'll just rewrite the equation. Y equals m times x plus b. The comparison is made in the following way. That the force that's being measured is comparable to y. I don't even want to say it's comparable to y. The force is y. On the other hand, x is 1 over r squared because that's what's being plotted on the horizontal axis. That means, continuing our comparison, that the slope of this mathematical line, which is the line that we're looking at on the graph, has to be accounted for by saying it's equal to kqq. And finally, whoops, the y-intercept has to be mg. So now, what we're going to do here now, Arden, is for any of these questions, if I said to you, what's k? And that's not what question 7 is. But if I said to you, what's k? You're going to look at the physics equation, and you're going to see that k is included as part of the slope. So in order for you to determine k, which you do, I think, in one of these questions, don't you? Yes? Okay. You would need to set the slope from your graph, whatever number that is, equal to Coulomb's constant times the product of the charges. In question 7, it says, well, what's the mass? What's the experimental mass of sphere stand 1? I think it's 1. Well, when you look at the physics equation, that mass is the highlighted pink part, which means it's related to the y-intercept. It's got nothing to do with the slope. So what we're going to do here is we're going to take the y-intercept and set it equal to mg. So what you do is you you determine the y-intercept of that line somehow. If you merely extend the, I don't even think you need to extend it. If you read this, it'd be nice if that was at 0.6, but I think it's a little higher than 0.6. Just to go through this scale again, because these graphical questions are really dirty on exams and on the diploma exam. You have to be very precise. So I want to make sure that everybody is on top of this. And I'll wait for the computer to catch up. Every square vertically is 0.4. Do you have a question, Shazmaida? Okay. Every square vertically is 0.4. So I'm actually going to highlight some lines here because they're getting a little grayed out as I expand it. So that bottom red line is 0.4, the top one is 0.8. So 0.6 would be halfway in between. 0.6 would be, and I'm not just being really, really picky for the sake of being picky. I really want to make a point. I think 0.6 is there, maybe, hard to move this, maybe there. Okay, maybe a little bit lower. I can't quite get it exactly in between. But the point is, it looks to me like that y-intercept is above 0.6. Then again, I don't think that y-intercept, if this is 0.6, if this is if this is 0.6, I don't think that the y-intercept is halfway between 0.6 and 0.8. In other words, I don't think it's 0.7 either. And if I really wanted to drill down here, I would say it's probably 0.65, would be my guess in reading it. I think 0.7 is not good. So if you said it was 0.65, and let's just check to make sure there are no other units here. It's not like times 10 to the something. It's 0.65 newtons. Then to answer this question, you would take your 0.65, set it equal to m times 9.81. And if you wanted to put units in, you could, but I don't care about the units. So what is 0.65 divided by 9.81? It'll be a little bit more than 65 grams. So 0.066 kilograms, which would be 66 grams, which is outside of my range, but that's why I said I'm going to change the answer so it reflects that. If you found the y-intercept mathematically, and you might, this is an interesting question, you might say, how could I not get the same y-intercept if I read the points accurately? Who knows? Who knows what your calculator is doing to find the equation of the line of best fit? What you would do is you would load in 2 points in your calculator from here. I think I looked at this and said 112, 12. And that may be where my y-intercept is coming out a little bit different, because if I look closely there, I think it's actually crossing not at 112. I think maybe it's 111 point something. And over here, I think when I did this, I don't know what I did. Let me do this one. 6, 1.2. Anyway, when I load those into my table and I do a linear regression, my y-intercept was like 0.61 something. Which if I divide that by 9.81, I don't get 66 grams. I get like closer to 61 grams. Anyway, have I answered your question? Well, let me ask you this question. What did you have? So you understand the principle of what it is we have to do, right? Okay. What did you get for a y-intercept? So I would say if you got 0.8, I'm just looking at the grid and making sure that the grid's not, that the grid is printed properly. You know, that it isn't wider over here than it is on the left. I would say if you got 0.8, that's outside of a range of acceptable values, I would say. Okay, so part of the problem, and this is hard for me to explain why you're not going to get as accurate as a line, but I guess I can explain it by going to extremes. Your points were closer together, okay? And if I take 2 points and have them relatively close together, I'm going to exaggerate my point to you. There are a whole bunch of lines that I can draw that go through those points. And because they're so close together, any little variation in them really changes the angle of this line. This is what I think happened. So you've got some error in reading any points. And if that error is on one point and on another point, and those 2 points are close together, those 2 errors, I mean, one of the errors might be too high and the other one too high, in which case your line is too high. One might be too high and too low, in which case your line is going to change angles totally, and the y-intercept will go way down. So I would try, it's a good learning exercise here, I would try to pick points that are really far apart. As far, not at the expense of being unable to read them. You still want to be able to read them well. Anyway, does that help? Okay. I think we pretty much covered the rest of this yesterday, so we're going to move on today and look now at lesson 2.6, which is potential difference. And we'll spend a couple of days, we'll spend today and Friday on this. We're going to be solving problems using potential difference. I don't know what page this is on, but you guys are smart. You can figure out where it is. I'll talk a little bit later about your written response and what you could have done to make it better. So we're solving problems using potential difference, and we have a warm-up exercise that we're working on here. It's looking like page 34. Is that what I'm seeing? Page 34. So we have a battery that's used to oppositely charge two parallel plates, and we're going to assume that any object I put between these two plates, gravity is negligible. So the mass of the object that we're going to be dealing with is very, very tiny, and it's not what I want to focus on. First of all, I have to talk about what the battery is. You can see on the right-hand side, this is the symbol for a battery. And you can see that the top has a negative beside it and the bottom has a positive beside it. But what you're going to find is that from now on, you will not be told that. So you need to know which end of that symbol represents negative and which represents positive. Now, in reality, I will very often just use this as a symbol for the battery, and that is acceptable. It's the short end that's negative and the long end that's positive. And you can kind of remember that because small is closer to being on a negative on a number line, and big is closer to being positive. Okay? Small is less than big, so negative is less than positive. The reason why we sometimes do that is that that's the symbol for a battery. Sometimes we do this, and all it means is you've stacked them. We've stacked a bunch of batteries together to get a larger oomph, I'll say. I don't want to tell you what it is just yet. So in fact, if you were to take a AA battery, don't do this because the chemicals are toxic and they're also corrosive. If you were to take a AA battery and open it up, you would discover inside of it, believe it or not, four or five, maybe 6 little tiny batteries. They look like watch batteries and they're stacked together. And that's why we typically have this symbol for a battery. So going back to this diagram, we have this situation. We have 2 points, point A and point B. Since the top plate is connected to the negative terminal of the battery, the top plate right now is negative. It's negatively charged. The bottom plate is positively charged. How does this happen? Well, is anybody in Chem 30 right now? Must either not be offered or it's offered right now. Has anybody taken Chem 30? So when you talk about electrochemical cells and you have those 2 half cells that are working to move electrons in one direction, that's what's happening here. There's a chemical reaction inside of this battery. We'll learn later it doesn't have to be a chemical reaction. It could be some other process. And it's pushing electrons towards the negative terminal of the battery. Okay. And since the electrons are all pushing away from each other, they're being held up there by a chemical reaction. That's a vast oversimplification, but the chemical reaction is pushing them up, so they can't go back down. But they're pushing away from each other, so if I connect this negative terminal to a piece of wire, to a plate, a metal plate, those electrons will spread out. And of course, inside of the battery is pulling electrons away from the bottom of this diagram, which means this is positive. Electrons in here will be attracted to that positive and move over there, leaving this positive. So we've got 2 parallel oppositely charged plates. It says we have a small sphere now with a charge of negative 3.2 times 10 to the negative 17 coulombs, and it's at point A. It's not moving, it's at rest. So we could draw it in if you like. We've got this sphere sitting here. It has a charge of negative 3.2 times 10 to the negative, did I say negative 7? I better look. 17 coulombs. I'm not happy with that diagram. I'm just going to do this. Okay, we don't even have to draw it. It's a little tiny thing, but it's sitting there. And the first question says, describe the electrical potential energy that the sphere has. Now, potential energy is a tricky little beast from Math 20 and also Science 10, but If I were to say to you, does this have gravitational potential energy? A good answer would be to say yes, because it has the ability to do work. It has the ability to do work on my foot. Because if I release it, it does work on my foot. The potential energy changes to kinetic as it moves through space. And then when it hits my foot, it applies a force on my foot, and then my foot moved a little bit, so there was a displacement. Force times displacement is work. There's potential energy. But if I were to ask you, does this book have potential energy right now? Gravitational potential energy. The best answer is to say no. And I don't want to personify inanimate objects. I don't want to personify inanimate objects, but the book has no gravitational potential energy because it's where it wants to be, right? If I just walk away from it, it's not going to do anything. Unlike it being up here, where to keep it up here, I have to actually actively apply a force to it to keep it in that position, don't I? I got to be pushing it upwards. So the question is, when we have this negative sphere at this location, how would you describe its potential energy? Now, it's potential energy because of electric forces, not gravitational. But since it's negative and it's at rest against a positive plate, it has no electrical potential energy. It's like having a ball at the bottom of a hill. It's where it wants to be. So the answer to this question is the electrical potential energy. Now, you've studied gravitational potential energy. You've studied elastic or spring potential energy. We haven't looked at this yet. At that point is 0. Part B says we're going to take that sphere and somehow move it. Pretty hard to move it without changing the charge, but let's imagine we had little insulated tweezers that we could pick that sphere up, and we're going to push it to the top plate. And we're going to move it at a constant speed, which is subtle but important. And the reason why it's important is I want to talk about the work done. Do you agree that work would be needed to lift that sphere to the top plate? Just like work would be needed to lift this book above the floor? Well, work is a transfer of energy. This is from Physics 20. This is really fishy. Energy equals the ability to do work, and work is a transfer of energy. These two definitions of work and energy are kind of circular. So when I get up in the morning, and I've strayed away from the question, but we'll come back to the question. When I get up in the morning and I eat my Wheaties or my breakfast or whatever I have, and I eat throughout the day, I'm putting into my body chemical potential energy. The energy in my body is increasing as I take that stuff in. But as I do work, the energy goes down. So if I lift up my backpack in the morning as I'm on my way out the door, I'm giving that backpack gravitational potential energy. I'm doing work to it. But what that means is the energy in my body just dropped by a little bit because I did work. Well, how do I get more energy back? Well, I ingest the energy, which is the ability to do work. But when I do work, all I'm doing is transferring that energy to something else. It's really just goes around in a circle. So when I talk about this is the amount of work done, this 6.4 times 10 to the negative 16 joules of work is needed to basically overcome the attractive force between this sphere and the positive plate and the repulsive force between the sphere and the negative plate. That much work is done to move it. I'm moving it at a constant speed, so the work is not going into kinetic energy. That's the only reason I have constant speed there. We're not talking about doing work to speed the object up. We're not talking about kinetic energy. And that means that the work must go into potential energy. Just like if I do a certain amount of work in lifting that book off the floor, when the book is at the top, where will that work that I've done be? Where will I have transferred energy to potential energy of that book? So the answer to this question is the work done is now electrical potential energy. So the sphere at A had no electrical potential energy, but when I get the sphere up to B, it will have potential energy. You agree if I take a slingshot and I put a rock in it and I pull it back, there's potential energy in that rock, in that system? Okay. Because there's kind of a springiness, right? If I let it go, it's going to fly. Do you agree that when I'm holding my phone above the floor, there's potential energy and I can feel the springiness? It's like there's an imaginary spring connecting this to the sky and it's pulling it or pushing it, right? Like a coiled spring. Or it's like a spring connecting the phone to the floor and I've stretched it. I can feel it pulling down. If I were to let go, it would go. Same thing here. If I were to put that negative sphere up here and hold it there, just with the tip of my finger, if I let it go, what would happen? Well, it would spring back down. But not because of gravity, because gravity is negligible here. We're not including gravity. Are you still with me on this? And I've set it up so it's the same direction as gravity. There's a force downward that we're overcoming. Okay. What is the change? This is baby steps, and it's probably pretty obvious, but what is the change in electrical potential energy from B to A? Well, if it had no electrical potential energy at the bottom, and the work done is the amount of potential energy I put into it, and this is the work done, then the change in electrical potential energy is that number. We could do it very clinically and say the change in energy is the final energy minus the initial energy. The final energy is the work done. It's the 6.4 times 10 to the, was it negative 16? Joules minus nothing. So the answer to this question is 6.4 times 10 to the negative 16 joules. And I know typically students at this point are going, yeah, so what? What's the point here? You're just dragging this out. We'll get there. Well, we're here right now. The point is there's this thing in physics, in electricity, called electrical potential difference, and it's defined very specifically. Electrical potential difference is defined as the ratio in the change in energy that a charge experiences to the charge. A ratio of one thing to the other means one thing divided by the other. So this is electrical potential difference. Sometimes we just call it potential difference. So potential difference or electrical potential difference is the change in energy that a charge goes through from one place to another divided by the number of coulombs. You can make a note here that electrical potential difference, and it's not potential, it's just potential. You can make a note that electrical potential difference is measured in joules per coulomb. It's energy divided by charge. And that's the formula. So let's use that formula to calculate the electrical potential difference between A and B when we move that charge. That would mean we have to take the change in energy divided by the charge. The change in energy was 6.4 times 10 to the negative 16 joules divided by the charge, which is 3.2 times 10 to the negative 17 coulombs. Just like with Coulomb's law, you would never put a negative into any formula for charge. So we're going to divide that and get what I believe is 20. But I'll give you a second to do so. Does anybody get 20? So the potential difference between A and B when that charge is moved from A to B is 20 joules per coulomb. Okay. So this next question is kind of tricky. If I go back and look at C, in order to move this charge, this is the energy required. Okay. I'm going to write that down somewhere. You don't need to write it down. I'm just going to remind us that if the charge was 3.2 times 10 to the negative 17 coulombs, the work required, which is the change in energy, was 6.4 times 10 to the negative 16 joules. Are those numbers right? The question, first of all, in F, is what if we move this charge instead? So how much work would be required? Well, let me ask you a question. Would the same amount of work be required to move this charge in F as the work was to move this charge in whatever letter that was? Is it going to be the same amount of work? And I think the answer is obviously no, but I want somebody to come up with a reason why the work will be different. Will the work be less? Will it be more? If it's more, why is the work going to be more? It will be more, by the way. Farhan? It turns out that's going to be true. So let me but that's not what I was after. Let me rephrase it. And I know where you're getting that idea from, but I don't want to expose your idea to others just yet. Without talking about energy directly, why is the work required to move this charge? And I'm doing this so that people watching a video later can see it. Why is the work required to move this charge more than the work required to move this charge? Without just saying, well, because the energy will be more. Pardon? Electrical what? Yeah, exactly. The force that you have to apply, we just finished talking about this a few days ago, can be found by taking the charge times the electric field strength. Now, I don't want to get into electric field strength between plates today, but since the charge is greater, the force must be greater. And since work can be found using force times distance, if you increase the charge, you have to apply a greater force. We're moving it through the same distance, plate A to B or whatever you want to call them, but if the force is more, the force times the displacement is more. So there will be more work required. And you can see it's a proportionality, can't you? Force is directly proportional to charge. So how many times more charge is the charge in F compared to what it was? Use your calculator and figure out what's happened to the charge. What I'm talking about here is what's happening to the charge when we go from this to that. And the answer is, I believe we're multiplying by 3, aren't we? So we don't need to show all of this work, but if you have 3 times the charge, you're going to have 3 times the force. If you have 3 times the force, you're going to get 3 times the work. So the answer to this question is going to be, we're going to take the 6.4 times 10 to the negative 16 joules and triple it. And get what I believe is 1.92 times 10 to the negative 15. So what's happening here is this got multiplied by 3 in going from the old charge to the new charge, which means this gets multiplied by 3 in going from the old work to the new work. So if we use that charge instead of the original charge, we have that much work. But look at the second part to question F. How much electrical potential energy is gained by that sphere? Well, the answer to that question is this number. This is a very subtle point, but if that's the work done, that's the change in energy. So the change in energy is also 1.92 times 10 to the negative 15 joules. If you have 3 times the force, you have 3 times the work, you have 3 times the change in energy. So now, using this formula that we have in D, we are asked to calculate the electrical potential difference now. The electrical potential difference equals change in energy over charge. So you're going to take the change in energy, 1.92 times 10 to the negative 15 joules, and divide by the charge, 9.6 times 10 to the negative 17 coulombs, to get the electrical potential difference. You get 20. And I think this is kind of where Farhan's mind was at, was that, to him it was obvious that ratio has to be the same. If you have 3 times the charge, you have 3 times the energy. It was a direct connection for him. But this is still 20 joules per coulomb, which tells us that this thing, this potential difference, has nothing to do with the charge you're moving. It has to do with the plates in the battery. So if I go back over here and I look at this diagram, the electrical potential difference of this battery is 20 joules per coulomb. So the electrical potential difference of the 2 plates is 20 joules per coulomb from one plate to the other. Okay. Later on, we'll talk about if I had asked you instead, what's the electrical potential difference from here to the midway point, it would only be 10 joules per coulomb because it would require half the work. So this number has nothing to do with the charges that we're moving around in our mind. It has everything to do with these plates and the battery they're connected to. So now to summarize this, and I used to just teach it this way, this would be the very first thing I would show you. Electrical potential difference is voltage. That's what this is, voltage. The symbol for voltage is delta V, not V. It's got to be delta. Okay. And this definition that we had, which is electrical potential difference, which I'm now calling voltage, is change in energy over charge, is the formula that's on your formula sheet connecting the energy, the charge, and the voltage. This change in energy can either be potential energy, like it was in our warm-up, or it could be kinetic, which we're going to see how that works in a second. Well, I'll explain it to you right now. If I take, well, we'll use this book again. We'll talk about this book that's on the floor, and I lift it using an applied force to this point. I have done a certain amount of work to the book. And if you're watching this video, I'm holding a book above the floor. And the work that I've done is now stored as gravitational potential energy, right? So the work done is the change in potential energy. But if I release this, it becomes a change in kinetic energy. It goes back to kinetic from potential. Similarly, and I will show this to you here, if I have an object at this point, I don't know why my pluses are not spread out. But I have my positively charged sphere this time at a positive plate. It'll be repelled. In our example, I think this was negative and we had a negative sphere, but it doesn't matter. All of the energy is potential. If I release it and take snapshots at a point in time, when it's at this point, it will have less potential, but it will have a little bit of kinetic. If I continue to track it at some other point, it's going to have even less potential and even more kinetic. And this is going to continue until it smashes into this plate. And I want you to notice that all of the energy is kinetic. Look at how much potential was lost. That blue thing. Look at how much kinetic was gained. That green thing, but they're the same, right? So what I can do in this formula is say delta E is kinetic or potential. It's not both. Very quick question. I'm not even going to write anything down here. Oh, we'll do this first. So we don't use joules per coulomb. We use volts. So in our example, it was 20 joules per coulomb. What I'm telling you is the battery in our example was 20 volts. It was a 20 volt battery. Quick question here. If I had a 12 volt car battery, what does that mean? It means that if I connect that battery to, say, a light bulb, for every coulomb of charge that flows through the battery in the light bulb, 20 joules of heat and light will be produced. So 12, not 20, 12. This is 12 joules per coulomb. So for every 1 coulomb of charge that flows in the battery, you're going to get 12 joules of energy being produced. So if I connect it to a light bulb, and we had 5 coulombs of charge flowing around in this circuit, then we would get 60 joules of energy because it's 12 joules for every coulomb. It would be heat energy and light energy. If I connected it instead to, this is a heating coil for a hot water tank, an electric hot water tank. If I connected it to that, then for every coulomb of charge that flows, 12 joules of heat will be produced. If I connect it to a fan, then for every coulomb of charge that flows, 12 joules of wind energy would be created. And the purpose of this example is to get you thinking of volts as joules per coulomb. I put those little caps on the V just to make sure you understand it's a capital V. It's not a vector symbol, it's just capital V. Any questions so far? Okay. So this example, number 1, is a set of calculations that I guarantee you will do at least 2, 3, 4 dozen times in the remainder of the course. It's something that keeps popping up. We have a device called a cathode ray tube, and essentially what we're doing is accelerating in the cathode ray tube electrons from a negative plate at the back of the thing to a positive plate at the front. This is an old TV. That's how old TVs work. They would have an electron gun. So if you want to visualize what this looks like, you have a little wire here, and this thing is charged negative. This whole thing is charged negative. Over here you have a plate that's charged positive. And we don't need to worry about why, but an electron is going to leak off of this wire. There's actually a secondary circuit in there that's heating up the wire so much that the electrons are just falling off. But since electrons are repelled from a negative and attracted to a positive, they are going to accelerate to the positive plate. The electron at this point in time has 100% electrical potential energy because it's forced away from this, and it has no kinetic. The question is, what speed is it going to have when it hits? And it's not a difficult idea when you see it. I'm going to take my voltage formula, which is potential difference equals change in energy over charge. And I'm going to put a K with the energy, because the change in energy the electron is going to experience will be kinetic. Okay? I'm going to now cross multiply. So Q times delta V equals change in kinetic energy. And then I'm going to alter this a little bit more and tell you or ask you to figure out why what I've written, although is correct and works, it won't always work for a question like this. Why am I allowed to just put 1/2 mv squared there for delta EK? Sienna, do you know? No? There's something it tells you about the electron's behavior in the question, that if it didn't have that, we would not be allowed to do that. Delta is not the same as a thing, right? Change in momentum is not momentum. Shazmaida, do you know? No. Did you say because it accelerates? No. There's something else. Liam? That's perfect. That's exactly it. Because in reality, everybody, delta EK, delta means final minus initial. What Liam said, in case the mic didn't pick it up, is that it starts from rest. So delta EK is that. In reality, what you should write is the following. Q delta V equals 1/2 mvf squared minus 1/2 mvi squared. That's what we have to get in the habit of doing. Now, if it starts from rest, which it does in this question, right? Well, does it actually say? It should probably say, but it's implied. They aren't moving. You know, the cathode ray tube isn't racing through space and then we accelerate them. It's sitting there and the electrons are just falling off. So because it starts from rest, VI is 0. If VI is 0, then this whole thing is 0, so we don't need to write it. So the charge, it's an electron, which is 1.6 multiplied by 10 to the negative 19 coulombs, times the voltage, which is 5,000 volts. Now I'm writing volts, but remember a volt is a joule per coulomb, isn't it? So the coulombs are going to cancel with the coulombs, leaving joules. This will be equal to 1/2 times the mass times V squared. And I want you to pay careful attention to this, because this calculation that we're going to do on the calculator right now is the one that you're going to see dozens of times. It's going to become so common that you'll see a situation like this. You'll see the accelerating voltage and you'll go, what's the speed? Oh, I'm going to do this calculation. You take the charge, 1.6 times 10 to the negative 19 coulombs, multiplied by the voltage. Did I get the voltage right, by the way? Is it 5,000? 5 kilovolts. Okay. But then look at the formula. I want to get V by itself, so I have to multiply by 2 to get rid of the half, and I have to divide by the mass. So I take Q times V, I double it, and then I divide by the mass. Now I can take the square root to get the speed of the electrons. So the answer to the question is 4.2 times 10 to the 7 meters per second. Any questions with example 1? All right. So number 2, an electron moving with a particular speed is going to enter a region between these two plates. So it's racing along at 2.5 times 10 to the 7 meters per second. It enters that little opening, and once it's inside of here, it's going to be repelled from the negative plate and attracted to the positive plate, so it will undergo a change in energy. It's going to accelerate. And we can solve this using the same formula. We want to find the speed that the electron's going to have over here. Change in energy over charge equals voltage. We can cross multiply. Q delta V equals change in E, which is kinetic, because it's accelerating. Which means we have Q delta V equals a half mv squared, and that would not work because it doesn't start from rest. It already has kinetic energy when it enters this region. It's going to be 1/2 mvf squared minus 1/2 mvi squared. I would like us all to calculate Q delta V. I'm not going to show the substitution. I'm saying just take the charge on the particle. Is it an electron again? Yep. Times the voltage. And I think you're going to get 4 times 10 to the negative, I couldn't tell you, 16? Yeah. So when you take the charge of the electron times the 2500 volts, you get 4 times 10 to the negative 16 joules. That's how much change in energy the electron experiences. That's the gain in the energy. I don't want you to worry about anything here. Don't worry about writing anything down here. If you want, you can just say this is the final kinetic energy, right? Let's figure out now the initial kinetic energy. So now we're going to do a 1/2 mv squared calculation. And I can't do that in my head. 2.5 times 10 to the 7. So I'm taking 0.5 times the mass of an electron times the speed squared. And I get this number. Do you get that number as well? Yeah. So 2.85 times 10 to the negative 16. I could be that kind of physics teacher who just says, okay, here's the formula, let's put the numbers in, let's calculate it. But I want you to think about what we're saying here. This is the change in energy. This 4 times 10 to the negative 16 joules is how much energy is added to the electron. This 2.85 times 10 to the negative 16 joules is how much energy, it was kinetic, but how much energy it already had. So if you had $285 in your pocket and I added 400, then you would add those numbers to find out your final money. Well, look at the math of this. EKF will in fact be the sum of these two numbers because this is minus, so you have to add it. It makes sense. It's not just some abstract formula with letters and numbers in it. So when I add that number to both sides, I get, and I'm pretty sure my math is right here, but you'll want to, or I want you to confirm that that's what you get. Okay, so how do you find the speed? Listen, how do you find the speed? You multiply this by 2, divide by the mass, and take the square root, because this is equal to 1/2 mv squared, right? So there's that the second of many dozens of times we're going to do this calculation. If you know the energy and you want the speed, double the energy, divide by the mass, take the square root. So I have to double that energy. Whoop, that's not right. I have to add 4 times 10 to the negative 16. So this is my energy. Times by 2, divide by the mass. Take the square root. You do have to hit equals after you divide by the mass. So 3.9 times 10 to the 7. Really, number 2 is done in the exact same way as number 1, except in number 1, we were able to ignore the 1/2 mvi squared because it started from rest. You know, probably 9 times out of 10 it will start from rest. It's that 1 time out of 10 you got to watch for. We have one more little thing we're going to cover here, and it's not that big of a deal right now, but it's going to become more and more important as we go deeper into the course. You know how in physics power is measured in watts? That's a standard scientific unit. But we have this alternate unit of power called the horsepower, don't we? And there's nothing wrong with saying horsepowers because sometimes it's more convenient. It makes a lot of sense too. If you have a 2 horsepower engine, it puts out the equivalent of 2 horses in joules per second, in theory, right? Not all horses are built the same. We have this alternate unit of energy, and it's kind of unfortunate that the name of it is electron volt. First of all, an electron volt, and the symbol for an electron volt is little e, capital V, is a unit of energy. It's not a voltage, it's a unit of energy. And very specifically, it's the amount of energy that you would have to get when you accelerate 1 electron through 1 volt. So if I have 1 electron and I accelerate it through 1 volt, how much energy does it get? 1 electron volt. Okay. One thing I want to point out to you, and you can write down this formula because we are about to use it, is that this formula only works with standard units. So this formula only works with volts, joules, and coulombs. There's no formula for electron volts. But the question is, how many joules is 1 electron volt? Well, 1 electron volt would be the energy gained. I'm multiplying charge times voltage when 1 electron is accelerated by 1 volt. So the change in energy when 1 electron is accelerated by 1 volt is 1.6 times 10 to the negative 19 joules. Not coulombs, joules. Find that on your formula sheet. 1 electron volt is equivalent to 1.60 times 10 to the negative 19 joules. Oops, what am I doing? There we go. Right there, middle of your screen, electron volt. 1 electron volt is that many joules. So we don't have to do that calculation all the time. Now, why do we want to use electron volts? Let's do the second example of question 3 now, the second part. An electron is accelerated from rest through 24 volts. What's the final kinetic energy in eV? Well, Look, the only tool we have at our disposal is this formula, right? That's how we calculate change in energy. And the initial energy is 0 because it starts from rest. So the final energy will be the answer to this question. It will be delta E. So we can take the charge, 1.60 times 10 to the negative 19 coulombs, times 24 volts. This will give us an answer in joules. I want to say 3.84 times 10 to the negative 18. Just keeping my brain sharp. 3.84 times 10 to the negative 18 joules. Okay. So that's great, but we want to know the energy in EV. So you have to now convert this many joules to electron volts. And I suppose we could set up a ratio. We could say that 1 EV is 1.60 times 10 to the negative 19 joules. That has to equal X electron volts over 3.84 times 10 to the negative 18 joules. So you're going to cross multiply there and find out how many electron volts of energy 3.84 times 10 to the negative 18 joules is. It's like we're converting watts to horsepower. That's a pleasing surprise when you see 24 pop up on your calculator, isn't it? We didn't need to do all this. This is the advantage of using electron volts. Electrons are very common in our universe and in physics 30. When you have an electron accelerated through 1 volt, if the energy is 1 electron volt, then when an electron is accelerated through 24 volts, it's 24 electron volts. And if you want to figure it out in joules, just convert it to joules. By the way, your converting between joules and EV will become more and more obvious every time you do it. You probably don't need to set up a ratio. How many of you would have understood that if this is the total joules and each electron volt is this many joules, that you would divide this number by the 1.6 times 10 to the negative? It's probably obvious to many of us, not everybody. So that's it. You still have about 15 minutes or so here to work on these problems. I'm saying 1 to 11. I suppose you could do every odd question. I would be happy with that. But ultimately, you need to know how to do every question. So if you don't do every question now, you should get them done later at some point. Ben, of course. So I hope that made sense. And to anybody watching this on video, I hope that helped out.